So thanks everybody for joining. I'm Marko Mäkelä. I'm lead developer InnoDB at MariaDB, and today I will talk about how InnoDB transactions and writes work and what kind of performance improvements we have made there. Oops, yeah, this is the first slide. So we are doing a deep dive, and we start from a rather high level. This is above the level of my talk, but we have this wonderful abstraction, the standard open systems interconnection model. And at the higher layers, we have applications, and then we have some encoding and presentation and session management. And then below that, we have something interesting, such as a MariaDB database running your web application. And inside the MariaDB server, we have upper layers like the client connection handling, authentication, and stuff like that. And then we have the SQL parser, access control, query optimization, and execution. And then it starts to get interesting. We have the storage engine interface where we can start and commit or roll back transactions. And then we have table cursors. We can open a table cursor. We can write, like insert a record, or we can search, or we can read a range of records and that kind of operations. And at the lower layer, we have at the lower layer, we have something that is interesting, like for the OSI model, we have the TCP IP or other transport layer, and the equivalent for that would be the InnoDB, which is sitting between the storage engine API or interface and the operating system. So the highlighted part of this slide is the topic or the focus of this talk. So we have the InnoDB transaction layer, which uses undo logs to provide atomic and consistent and isolated access to tables. And it also uses transactional logs and creates read views based on undo log records. And it supports distributed transactions. Underneath of that, we have the InnoDB mini transaction layer, which is basically allowing atomic and durable changes to multiple data pages in a single mini transaction. Somebody is not muted apparently. Then we have a page checksums and crash recovery. It's also part of the mini transaction layer. The crash recovery is what we actually need the mini transactions to be atomic for. And below that, we have an operating system and file system block cache, which is what we are interacting with. And the levels underneath don't really interest us. We assume that the operating system gives us some block-oriented storage. So now we are diving to the deepest level, to the block level. So how do we manage relational data on block-based storage? Actually, you don't need block-based storage. You could have something like RocksDB, which is using append-only LSM trees, but we are more traditional, and this is block-level storage. So you could have heap organized tables like we have with MyISAM or area tables. In those tables, the records or the rows are stored separately in a heap, which could be an append-only file. And then you have separate index trees, which are page-oriented, and they contain keys along with heap positions, like row ID. It could be a file offset to a sequential file that contains the records. In InnoDB, we have index-organized tables, and we have index B trees. So we have a clustered index that contains the primary key of your record, and then the user columns. And there are also some system columns, the transaction identifier and the undo log pointer, which we need for rollback and for log checks and for MVCC, which is snapshot isolation, non-locking reads. And inside the InnoDB secondary indexes, we only have the secondary index key and then the primary key. So if we have a table that contains primary key A and a unique secondary key B, then in my ISM we would have the heap would contain all columns A, B, C, and then the indexes, we would have two indexes, one for A and one for B, both pointing to the row ID. And inside InnoDB we have the clustered index record with the key A, and then the system columns, then the other user columns. And then we have a secondary index record which contains just B and A. The basics of B trees are shown in this slide. It's not exactly matching InnoDB because this example doesn't show the system columns. But the basic idea is that we have pages that contain n keys that are ordered by the key, and these keys could be also prefixes or key paths. And then we have n+1 pointers to lower level pages that could be non-leaf or leaf pages. And at the very bottom we have leaf pages that actually contain the data. Okay, there is some variation, but the InnoDB stores the data directly in the leaf pages, not pointers to data. So if you have a table with a variable length primary key A, then we could have something like this, that in the root page we have pointers. We have pointers to 3 pages that happen to be leaf pages in this case. So anything smaller than the key Fi will be in the first child, and then anything between Fi and I are on the second child, and then anything greater than I will be on the third child. This is the nice property of this is that it's a balanced tree. So if you have whatever data you are throwing at it, it cannot degrade to something like a linked list of pages, which you could have with binary trees. But on the other hand, there is a drawback that we could have lots of empty space on the pages. The fill factor could be low. Fill factor is also a good thing because if you are inserting something into the middle, then you can avoid a page split if there is some spare space in the pages. But it's also a bad thing if you are doing like a table scan, you will have less payload in the pages. So you're accessing more pages to actually get your data. In InnoDB, there are also other data structures inside the data files. So basically, InnoDB data files contain files within files, and there is some management of page allocation. There could be some freed space inside InnoDB table spaces. For example, if you delete a lot of rows, then the pages could be freed inside the table space, but InnoDB never shrinks the files. There is only some exception related to truncating undo log table spaces, but normally the only way InnoDB files can shrink is when you rebuild the table space, like optimized table. So we have allocation bitmaps that tell us which pages inside the file are actually allocated for something. And then we have file segments, which are lists of pages that contain numbers of pages that belong to a particular subfile, so to say, or inode, it's called in InnoDB source code. So for example, in each index tree root page, we have pointers to the top segment and the leaf segment. The top segment contains all the pages that are allocated for non-leaf levels, and the leaf segment contains all the leaf pages and all block pages. Then we have tables, of course, in table spaces. Those are simply collections of index trees. And each index tree starts at some root page that cannot be moved. So when we split the root, we actually we retain the old root page number and we move the contents to new pages. And in InnoDB.ibd files, the clustered index root page always is at page number 3. For the data dictionary, we have some hard-coded index trees inside the InnoDB system table space. These 4 tables that contain the definitions of tables, columns, indexes, and fields are hard-coded. And there are also some other system tables like sysforeign calls, which contain foreign key metadata. And these table definitions for these tables is stored in these 4 tables normally, just like any user table definition would be. And finally, we have, for transactions, we have a transaction system header page, which in the current MariaDB implementation, it's only a directory of rollback segment header pages and undo logs. So that the page is never modified, except when the undo tables, number of undo table spaces is being changed. So it's just a directory. And the undo logs themselves can be in separate table spaces or inside the system table space. The default was changed at some point so that we have 3 separate undo table spaces by default. Now we are coming up 1 layer to the mini transactions. So how do we manage the atomic changes to the pages? A mini transaction is basically a context within you can acquire buffer fix or page latches on buffer pool pages to read or write those pages. And any pages that are written or modified, we must write log for those pages unless they are pages inside the temporary table space. So the mini transaction also manages the log records for any modifications. And when the mini transaction commits, it will release the page latches and it will write the log to the global storage. That will be shown in a further slide. For example, we have the concept of optimistic operation in InnoDB. If we insert a record normally, or in the optimistic case, the record will fit in a B3 leaf page. We can just modify that single page and that's it. But it's not that simple either. We need to do multiple atomic changes on that page. It's not just writing the record itself. We also have to update some record header fields to say that now we have this much free space left on the page, and here is where the next record could be allocated from, and also next record links and page directory. So all those changes have to be done in an atomic mini transaction. And in case the optimistic operation is not possible, for example, if the record contains blob columns, or if the page has to be split, or if you are deleting a record and page needs to be merged, it's becoming empty, then we have to revert to a pessimistic operation. A pessimistic operation is that it will acquire latches on multiple pages and it may split or merge some B3 pages. So in the case of insert, it would at least add 1 more leaf page and insert a new node pointer record to the upper page. It could also happen that the upper page needs to be split as well. So the worst case is that the B3 will grow in width on each level. So it would grow by the height of the tree, and we would add 1 more root page level. That's the worst case for pessimistic insert. And these changes, they need to be atomic. So all the pages that the pessimistic operation modifies need to be committed at once, or nothing. We must recover either all or nothing, or all changes or none of them. There is also a constraint that the mini transaction can modify at most 1 index B3. And it may also write an undo page to record a undo log record about that change. But it must not modify multiple indexes. The reason for that is that for read operations, we need to be able to read from two indexes in the same atomic mini transaction. So when we are looking up some record by the secondary key, we may need to look up the primary key, and then we may need to check some undo log pages to fetch the correct version of the record. If we allow the modification operations to use multiple to modify multiple indexes atomically, then we would have a situation that the modification operation is holding a clustered index page latch, and it's waiting for access to some secondary index page. And at the same time, we would have the read mini transaction holding the secondary index page and waiting for the clustered index page that the modification is holding. So that would be a cyclical wait and a deadlock between those threads. So that's a lock order inversion or latching order violation, as Heikki Tuuri, the inventor of InnoDB, preferred to call it. Undo log pages are safe to access for read operations even without holding any page latch, because the format is such that whenever we write to undo log pages, we will not overwrite any existing data. And the only way we can reuse undo log pages is when a purge operation is cleaning up, and at that point we cannot have any read operations accessing that page. So an insert operation, even if we have a single row insert transaction, it will necessarily involve at least two mini transactions. One mini transaction to write the undo log record for inserting the record, and then optimistically inserting the record into the cluster index. And then we would have to have a separate mini transaction to mark the mini transaction as mark the user transaction as committed in the undo log header. And if there are any page splits needed, then we need to run further mini transactions for pessimistic insert. And if there are secondary indexes, we need to run a mini transaction for inserting a record to each secondary index separately. So it could be really many mini transactions to execute a simple insert of a single row. The main purpose of the mini transaction is to have atomic recovery. So there is a other competitor who says that the log is the database, and the data pages are basically just a cache of the log. Well, we don't take it that far in InnoDB. We normally truncate the redo log in checkpoint operations. So even though the log itself, it's the definition of the state of the database, we are doing some shortcuts by this checkpoint. So we are, from time to time, we are moving, we are kind of discarding old history of the write-ahead log. The purpose is that we will save space. We only have a fixed size redo log in InnoDB. We cannot keep more history than the size of the redo log. And we also save time in case the database is killed and restarted, because recovery would have to process all the log from the latest checkpoint to the current end of the log. So the checkpoint will ensure that there are no unwritten page changes that are older than the checkpoint LSN in the buffer pool, and then it will advance the checkpoint header to that log sequence number. Recovery would apply all changes between the latest checkpoint up to the end of the file. And this end of the file is not actually the end of the operating system file. It's somewhere in the middle. We have this circular file. So at some point we notice that there is some kind of a checksum mismatch or a sequence number mismatch. And then we know that, okay, we have reached the end of the log. what we are seeing is something that was written earlier before this latest checkpoint, some garbage. And the recovery will recover all pages to match the latest complete mini transaction. If we got some records of a mini transaction, but not the whole mini transaction, then we must discard that. It should also be noted that we have write-ahead logging, so it's never allowed to write any persistent data pages before the corresponding log record has been written. So here is a picture about the mini transactions and crash recovery. The mini transaction comprises two things. One is a log of anything that has been logged or latches held by the mini transaction. In a pessimistic operation, we hold an index tree latch to protect the upper level non-leaf pages of the index tree. If we are allocating or freeing any pages, then we hold a tablespace latch. That's protecting the allocation metadata. And then we, of course, hold latches on buffer pool pages. In this example, the blue blocks are those that the mini transaction has modified. So there is a log record covering these blue pages. And the white ones are some that have been accessed but not modified. At the mini transaction commit, we will copy the local mini transaction log, which describes the changes. We will copy that to the global read log buffer. We will obtain a log sequence number for our mini transaction, both the start and end log sequence number. Then we will, if we were first time modifying some previously clean page, then we would update the oldest modification field of that page descriptor and add the page to the flush list. But if the page was already dirty in the buffer pool, then we just we only update the page LSN field in the page header. This LSN field will be used for crash recovery to compare if a log record needs to be applied. Only if the page LSN on the data page is smaller than the LSN that we get from the redo log, then we will apply the change. So once the mini transaction has copied data to the redo log buffer, it may release all the latches, and then at some later point, some thread will write this log buffer to the log file, and after that, we may write blocks from the flush list to the data files. And when we write from the flush list, the page LSN must never be newer than what we have already durably written to the log. That's the write-ahead logging constraint. Okay, now we are ready to backtrack to the transaction layer, which builds on top of this mini transaction. So the InnoDB transaction layer is optimistic. It checks things and applies changes on the go. So transaction commit is basically instantaneous. We just mark the transaction state as committed in the undo log header. But if there was any problem like a deadlock or a duplicate key error or a log wait timeout, then we need to roll back the changes that we already made in this transaction. So we need to revert or apply the undo log in reverse and then commit the empty transaction. That can be very expensive, of course. The transaction layer relies on the mini transactions performing the atomic operations that I described in the previous slide. So we can assume that the index trees will always be in some consistent state, but we cannot assume that the indexes of a single table will be consistent with each other. It's a responsibility of the transaction layer to make it appear so. On startup, after the mini transaction recovery has been executed, then the transaction layer will recover any incomplete transactions from the undo log pages. And it will also recover their logs on any modified records. Basically, implicit locking means that if an index page contains a transaction ID that belongs to an active transaction, then the record is locked to that transaction. We have an automatic rollback of incomplete transactions in the background, but that doesn't cover any distributed transactions that are recovered in the XA prepare state. Those transactions will have to wait for an explicit XA commit or XA rollback statement from a client connection or from the bin lock, which is using the XA mechanism to keep the bin lock in sync with InnoDB. The transaction layer supports non-locking read or multi-versioning concurrency control by read view snapshots that are based on undo locks. So how do we get atomic, consistent, isolated, and durable transactions? The undo lock is basically the glue to make this happen. We have a write-ahead undo logging. So before modifying any indexes, the transaction must write an undo log record saying that I'm going to insert this primary key, or I'm going to update a record that contains this primary key, and it will affect the update will affect these columns or these secondary index keys. Same for delete. So the undo log is usually row level, but there is a special case for inserting data into an empty table. In that optimization, we just write a single record into the undo log saying that if this transaction needs to be rolled back, then we just truncate this table or partition. And then we will obviously use table level locking to cover the insert. The read view for snapshot isolation, it's basically a set of transaction identifiers that were committed when the read view was created. And if you have any non-locking reads that make use of the read view, they may need to access undo logs of other transactions, either ones that are still active or ones that have been committed, but history hasn't been purged yet because we have an open read view that may see the history. Once there is no such old read view that prevents any cleanup, then there is this purge subsystem that will remove the undo logs for committed transactions. And also it will remove any delete marked records in the indexes. So when you update a key in a secondary index, for example, we will delete mark the old key and we will insert a record with a new key. And same, if we delete a record, we will only delete marked it. And only after the purge, the record will be really deleted. The purge is also covering DDL recovery. For example, normally a drop table operation would remove the file. But if the drop table was committed and the server was killed before it got the chance to delete the file, then in that case, we would delete the file in the purge after the server starts up. Here is a page view of the transaction layer. What kind of pages we have in the buffer pool. So we have the transaction system page in the system table space. It's only a directory to these persistent rollback segment headers. In MariaDB, we have 128 rollback segment headers, and we have a separate set of rollback segments for the temporary table space. So the rollback segment headers pages, they contain references to transaction logs of active transactions. And then there is this history list where we attach any undo log from committed transactions. Tables consist of indexes. And in this illustration, we have a B3 index tree of the primary key. We have the root page. It contains some pointers, and then we have some non-leaf page in the middle, and at the lowest level we have the leaf pages, and there we have the primary key values. We have the transaction ID, and the undo lock pointer, and then user columns. For a non-locking read, if we see that the transaction ID is not in our read view, then we will look up the undo lock. It can belong to an active transaction or a purge or a transaction in the history list that hasn't been purged yet. And for lock checks, if we check for if the record is implicitly locked, we look up the transaction ID in a main memory data structure. If it exists there and the transaction is not in committed state, then we know that, okay, we have to wait for a lock. We will create an explicit lock on behalf of that transaction. Okay. So the locks and the undo lock are the glue that make this mini transaction layer appear atomic and consistent for the SQL layer. Like I said, modifying a row in a multi-index table is not atomic. It cannot be atomic. So we work around this effect by making some extra steps when accessing secondary indexes. In MVCC checks and in purge, as well as in implicit lock checks in a secondary index, we may have to look up the transaction ID via the primary key, which we have in the secondary index record. If we had a per record transaction ID in secondary indexes, then lots of things would get simpler, but we don't have that yet. So MVCC and purge may need to retrieve old undo lock records. If the undo lock pointer says that it was a freshly inserted record and not an update of an existing record, then we can say that, okay, this transaction ID doesn't belong to my view. It was a fresh insert. I will just ignore the record. Otherwise, we will have to fetch the undo lock record and construct an earlier version and repeat until we get to the transaction ID that belongs to our read view, or we see that, okay, this whole record was inserted after my read view was created. Also, blob operations are not atomic. Same applies to text and long varchar columns. Even an update operation that is not updating a blob column, it may move some existing column to off-page storage. So that's handled by undo lock. But the effect of this is that read uncommitted transactions may see truncated blob contents. Any other transactions will see a valid pointer to a blob because they will fetch an earlier version of the clustered index record, or they will acquire a lock on the record, and then it necessarily cannot be. There cannot be any blob operation in progress. Okay, now coming to the performance part of this talk. So it's always a challenge with performance optimizations. What can you do, or what is reasonable? I think that in general, the InnoDB design is rather reasonable. We have page latches which are held for a short period of time. Typically, the longest time is when we have to wait for a page read into the buffer pool. Could be a few milliseconds. And then we have this transactional row level locks, which can be held much longer. This gives a nice level of concurrency if you compare to my ISAM or area where we have table level locking, or if you compare to SQLite, which has database level locking. We have much more concurrency in InnoDB. But it's not perfect. Before MariaDB 10.3, we had a separate mini transaction for creating the undo lock for a transaction and writing the first undo lock record. That didn't make any sense because this undo lock would be completely invisible to other threads until we write anything to indexes. So currently do all this and try to do the optimistic operation in the same single mini transaction. There is this problem that update and delete operations will first execute a locking read in the storage engine API. And this locking read will create an explicit lock object and release the page latch. If we had some way to retain the page latch and execute the update or delete directly on that page, then we could avoid creating the explicit lock, and we could just rely on implicit locking, meaning that if the transaction ID in the record belongs to an active transaction, then others know that, okay, this record was updated or deleted by another transaction, and that's it. There are some optimizations, like MariaDB can release unmodified pages in the middle of a mini transaction, and it can also release the latest pages. In original InnoDB, we would, for no good reason, restart the mini transaction and do some extra work and extra page lookups. But we are avoiding that, some of that in MariaDB. Also, if we need to restart a mini transaction, like sometimes if we need to make sure that the lock checkpoint can advance, in that case we have to release the page latch, give the lock subsystem a chance to go a bit ahead. In that case, we can hold a buffer fix on the page, and the buffer fix will prevent eviction of the page, and then we can avoid looking up that page again when we restart the mini transaction to continue further. There is also some work in progress to optimize some cases where Heikki thought that, okay, we have this lock order inversion, we must release everything and start from the beginning. One example is the reverse index scan. It's doing lots of busy work. In the optimistic case, we can just move to the previous page because the page that is not occupied. We can just try to acquire it, and if the lock is available, fine, we can just move to that page. There is no deadlock with another thread doing a forward scan. But if you have to wait, then of course we have to release everything and do it in the hard way. Some more performance optimizations that have been done. I already mentioned this read-only transaction system page in MariaDB 10.3. We also have a lock-free hash table that keeps track of the active transactions. There used to be a transaction system mutex which was quite hot, but we don't have that anymore. We just have this log-free hash table. And we also merged the separate insert undo and update undo logs to a single log. In 10.5, we got a completely new redo log record format. It was designed to be more compact and easier to parse. And the recovery has a custom allocator so that it can release some memory that is reserved for the log records in the middle. And there will be fewer recovery batches if you are using a small buffer pool, or if you are doing a recovery with a smaller buffer pool than the server that created that was used before the server was crashed or killed. Then we have a special records free page which indicate that some pages were freed from a table space. When those records are written, we can avoid writing back the garbage. So basically we are freeing page. It doesn't matter what the contents was. Recovery doesn't care. We are not going to access that page. Also, we are skipping the double write buffer for pages that have been reinitialized, and recovery can recover the pages without reading them. All page writes in 10.5 are asynchronous, including the double write buffer, and we use all 128 pages of the double write buffer for actual operations. In MySQL 5.7, this double write buffer was only used with synchronous writes and 64 bytes at 64 pages at a time. So we have more capacity for the double write buffer. In 10.6, the latches and transactional logs were rewritten. And then there is an optimization that we can access the undo log records directly in the buffer pool via buffer fixed pages. We don't copy them to heap anymore. The purge coordinator task is looking up all the pages for the purge workers. And this can run concurrently with undo log truncation. So we have a much faster processing of records with fewer conflicts between the purge threads. In 10.8, we got a new redo log file format with a variable block size. And this allows more concurrency when writing the log. In InnoDB, we have both logical and physical logging. The undo log pages are mostly logical. We identify things by table ID or virtual index ID or by keys that are affected. But the only exception really is that the block pointers are physical. When a record that contains a blob is deleted, then it's the purge that will actually remove the blob object, and that's why it needs the blob pointers. The redo log is physical mostly. We have, for all records, we have the tablespace identifier and the page number, and we have the type and length for all records explicitly. In MySQL, the length is implicit, and you need to do more parsing to find where the next record is starting. Recovery will find any modified files based on special records. So if you delete a file, you will write the file name and the tablespace ID, and then after that you can delete the file. Same for rename. And this file modify record is special. It's written for the first time we modify some tablespace after the latest checkpoint. Some operations use logical format, like if you insert a record into an undo log page or insert a record into an B3 index page, we use a special format so that we don't have to write so much physical log for updating all the page headers. The log application will take care of that. The InnoDB log file, there is only a single file in current MariaDB versions. It's circular and it's pre-allocated. This allows very fast in-place writes in most file systems. So if you have an O direct write to the log file, the fsync will basically be a no-op. So it really is enough to write the log blocks themselves. Recovery is possible if the log write doesn't overwrite itself. So we are a bit anxious about that. So if you configure a too small InnoDB log file size, then there will be frequent checkpoints. We have to write pages from the buffer pool to the log file to avoid this situation where the log has been kind of corrupted. And this causes some write amplification. It could be the case that all your data fits into the buffer pool, but and most pages are dirty, but you have to write back those dirty pages just because you have a too small redo log file. If you had a bigger redo log file, you could just keep writing redo log and not write any pages because all the workload fits in the buffer pool. Up to MariaDB 10.6, we had half a kilobyte log block size. And there were two properties. One is a nice one, that a concurrent backup can easily keep up with the server. It just uses a log block parser and computes checksums on the half a kilobyte blocks. Nice. But what was not nice is that only one thread at a time can append to this global log buffer. And it's holding this logsys mutex also while doing some time-consuming things such as encrypting the log block or computing the checksum. And this is blocking all other threads which would like to write to the log. So MySQL 8.0 solved this problem by completing new redesign of the log format. but we chose something else in 10.8 or in the current 10.11 long-term release. I gave a talk about that on FOSDEM 2022. So basic idea is that instead of having these fixed size redo file blocks, we make each mini transaction a logical block on its own. Mini transaction size could range from about 10 bytes to the maximum size of 2 megabytes. I also managed to shrink the log block header from 96 bits to a single sequence bit number. So the sequence bit is flipping each time this circular log file wraps around from the last byte to the beginning right after the headers. And this sequence bit allows recovery to detect the wraparound or the discontinuity point when we are switching from the actual end of the log to some garbage that had been written before the checkpoint. And with this, we have a truly concurrent execution of multiple mini transaction commit. Before any like disturbing locking, the threads that are executing mini transaction commit, they are computing their own the checksum of their own log even before they know the final log sequence number that will be allocated for them. And once they have allocated the log sequence number and the position in the log buffer, then they may concurrently copy their own log to this shared buffer. And that's covered by a shared latch on the log system. So we can have multiple threads appending their local log records into the global buffer at different points of the buffer. Well, this had to be optimized further. Originally, it was the idea of Vlad Weintraub to do it. I didn't come up with this in the first place, using a shared latch to protect the concurrent writes. But the allocation of the buffer and the LSN, it used to be covered by a mutex that protected several feeds. And this turned out to be a huge bottleneck. I tried to revise it a little bit by implementing a spin loop only variant of the lock, but that didn't help much either, or it would, on some system it would be a huge regression, and on others it would help things because it could avoid thread context switching. Finally, in a recent release, I think 3 or 6 months ago, we released a version where we are shrinking this critical section of allocating the buffer and advancing the log sequence number to a single instruction, basically. An atomic fetch add of the size and a constant that increments another counter. Yeah, we have these users who are obsessed with having lots of counters, and we have this counter which is counting writes to the log buffer. I'm not a friend of that, but okay, I imagine that we can do some kind of SIMD programming. We can pack multiple things into the same 64-bit field. So we have about 33 bits, I think, for the size part, and then we have some 30 bits for this counting the write requests, and then we have a flag, a backoff flag. If this critical section of the optimistic case is overflowing, we are running out of the space that we had for the buffer. We need to actually write the buffer to the log file. Then we have a flag to indicate that. So in code, it looks like this. It's a bit, lot of C++ code, but actually it's much smaller if you look at the machine code. So at the start, we atomically add our size and this magic constant to this 64-bit number. And then we mask the size part of the result. And then we check if we got an overflow or if we got this back-off bit set. It's also allocated in such a location that this overflow condition will hold. So if we got the unlikely case that we have this overflow. Then we will first execute one more atomic operation to set this backoff flag. Recent versions of GCC are very nice. They can optimize this special case that we are setting and checking a single flag to this special instruction. Older GCC versions before GCC 7 would actually create an ugly loop around lock compare exchange, which is not what we want. And after we have set this flag, we can subtract our size. It's either the lock x@, or lock sub, which will be used for that. And then we call a non-inline function that will actually do the magic for writing to the file and ensuring that the backoff flag has been cleared. Once that function returns, we try again, add our size, and finally, I omitted some details. We will return both the LSN and the buffer position to our caller. So this L in this call is what we read from the global field in the atomic fetch add, and we will just apply it to some data members which are protected by the locksys latch, which we are holding in shared mode. So that's pretty nice. And this gave a huge improvement. I don't remember the details anymore. Steve showed it some benchmarking. I think it was most prominent on a high-end machine where we were using more threads than a single CPU socket. Obviously, this single instruction is much less overhead than going to the operating system kernel for some few text weight and so on. So there are some uses of exclusive locksys latch, and those uses are of course nasty because they block all the writers and so on. We have this member function get LSN. Now it needs to hold the exclusive latch because we removed the previous atomic field locksys LSN in this fix that I implemented. But luckily this function is only called in cases where we are already holding the exclusive latch for other reasons. Then there is this approximation, lock-free approximation that we are using for heuristics in the adaptive flushing to determine how many pages we should flush. In that code, we definitely don't want to acquire the locksys latch. And we also need exclusive locksys latch when we are writing to the actual log file. So we must shortly freeze this buffer, make a snapshot of the buffer, kind of. We swap the buffer with another copy, and then we write the other copy to the file system. And when we are holding the exclusive latch, we also reset this offset so that the concurrent writers, they can resume as soon as we release the locksys latch, they can resume writing to the other buffer once we have done the swapping. Only in DDL operations that write file names or in checkpoint operations, we will retain the locksys latch across the file system operation. But in normal DML code path, we will let the concurrent mini-transaction writes to resume while we are writing to the log file. The log file writes are covered by special group commit logs, which were implemented by Vlad Weintraub in MariaDB 10.5 and 10.6. So that's you can thank him for the efficient group commit logic. There are some notable changes I would like to mention about the buffer pool. As part of getting rid of the locksys mutex and adding this more concurrency-friendly log file format, we also got rid of a flush order mutex. So this was a bottleneck for mini-transaction commits as well. But now we allow multiple mini-transactions to really commit simultaneously. What we need to compensate, we must do some sorting when we are inserting blocks that were dirtied for the first time, when we are inserting them to the flush list. But this is a rare case. Usually pages are being modified over and over again, so they will already be dirty in the buffer pool. There was a sorting help, buff pool flush RBT, a long time ago, but we removed it from MariaDB. It was basically only used in crash recovery. In MariaDB recovery, in the last recovery batch, we will sort the flush list. But in previous batches, we just flush we empty all the flush list, and we don't care how it is sorted because we are not doing any log checkpoint, so the order doesn't matter. The order matters for the oldest modification logic which the checkpoint uses. We also skipped the double write for pages that were reinitialized since the latest checkpoint. I don't remember, was it 10.5 or 10.6 where we got this one. In 10.6, we got more concurrent crash recovery. So we have also fake read operations. We are using multiple threads to recover pages that can be recovered based on log records only. I think that before some MariaDB fix in 10.2, we were unnecessarily reading pages, even though we knew based on redo log records that we are actually initializing those pages. So this is a speed up also. But before this fix, these special pages were recovered in a single thread, so it could be slow. Then there was a change that the double write buffer will actually write pages that are newer than what has been written to the log file. This is okay because the double write buffer is only a recovery aid for pages that are corrupted because the server was killed in the middle of a page write. So the double write recovery logic is checking that the LSN in the copy in the double write buffer must be between our checkpoint and the end of the log. If it's outside that region, then the copy of the page will be ignored. So this is safe to write anything newer to the double write buffer. And then there is a future task to make use of the atomic writes interface in Linux 6.13. I don't think it's really implemented for all file systems yet, and also a challenge is that there are very few storage devices that would, for example, advertise supporting 16 kilobyte atomic writes, which we would need for the default case, 16K page size. But that's something that I'm looking forward to. It would basically allow us to safely disable the double write buffer. So that was all I had in this presentation. I'm very happy to answer any questions. I guess one question could be, where are the performance benchmarks? I'm sorry, maybe I should have included something, but I guess we will have blog posts about those.
Yeah, Marko, no question, but I think it's a great presentation, and yeah, but I think too much is covered for this short part, so I'm not sure how much people have got really of the details of the mini transactions and the physical and the logical layer. But yeah, it's a very good presentation covering a very good part of InnoDB, especially the physical and logical separation within InnoDB is something really a great thing to explore for anyone, because the mini transaction infrastructure or the physical layer actually allows you to build a different system actually, which is non-relational or whatever, and still be ACID. Maybe the interface is not that clear, but it is by design actually achievable. So that's a very fundamental of the mini transaction layer. And
right.
Yeah.
Right, we could also have a different format of undo log on top of the pages. There is no real reason why it should be B3s exactly, or why we should use optimistic transactions. We could also use the same thing with some different design with pessimistic transactions.
Right. Although I think it is never tried, but in reality it is possible. It's very powerful and nice design, and maybe it deserves more time, I think. But it of course depends on people interest. But it's a great presentation, Marco. And I don't still completely understand the performance optimizations here, and I am more familiar with the 8.0 optimization, which kind of goes parallel, solving similar problems but slightly different way.
Right. So one approach that I took with MariaDB is that instead of splitting bottleneck mutexes like the buffer pool mutex, the solution in MySQL 5.5, I think, was to split the buffer pool into multiple buffer pools. We went to a single buffer pool and we went to remove bottlenecks on the single buffer pool mutex. Similar for the file system mutex, it was split in some version of MySQL 8 so that there would be less contention. But what we do is make more use of atomic operations and try to acquire the mutex less often. So it's also that kind of small optimizations to keep things as simple as possible. Use a single circular log file instead of multiple files like MySQL. That was
right. That's actually very nice, I think, because when MySQL 8 multiple files we did, the purpose was not actually solved with the multiple files, although it was advertised in a different way. But the main reason why we go for multiple files was basically it was not much different from the single file thing or two files.
Yeah, well, the two files were basically just a single file treated as split into two parts. Okay, I guess this was mostly.
Marko,
yes, Andre, please.
Just one thing. Do you consider to take contributions from MySQL? Contributions, of course, in double quotes. So some feature that they have developed and advantageous.
Sure. For example, the log system rewrite in MariaDB 10.6 is based on what was done in MySQL 8, but it's a bit different. Different data structures and some refactoring that has been done in MySQL we have omitted. It's of course a matter of taste. Do you like to add some modern C++ abstractions on top of everything, or do you want to keep it more low level? But so it's not possible to really take changes directly from MySQL, but ideas, of course, can be applied when they make sense. Okay, nobody else. I guess this went over the top of the head of much of the audience, just like the previous deep dive talk I gave in 2018, and that was at a higher level, focusing more focusing also on the SQL side of things. So if there are no questions, then I guess I will just thank you for your time, and I hope that with time, when you watch the recording and download the slides and follow the hyperlinks, it will maybe get a little bit clearer. So thanks everybody, and have a good evening or morning or whatever time of day. Thank you and bye.
Thank you. Bye-bye.
The MariaDB Foundation is the global contact point for collaboration on MariaDB server. Our work is made possible thanks to the support of our sponsors.